So, hello. That looks kind of cool. I don't know whose idea that was, but it was a pretty good idea. So, welcome. Thank you for coming. My name is Shahir Shahrabi, and I would like to talk to you about one of my favorite hobbies, which is painting with code using programming. I will be covering what a painted piece is that's made with code, and then go over why I do those, and as well cover maybe how you can also make something like that. But first, a short introduction. My name is Shahir Shahrabi. I am an Iranian programmer. Currently, I'm the creative lead in Realities.io. In the past few years, I have done many different types of programming. I have done everything from native apps with C++ to graphic programming, which is writing graphics for programs for the graphic card. You can see some of those there. I like to share my code. I like to give talks like these. I like to write blog posts where I talk about these techniques. If you would like to know more, please head to my page. You have all the info you need. Now, enough of that. This is a moving painting. Okay, the contrast is pretty good. I was worried about the beamer, but it's pretty good. So, why is it a moving painting? This painting is done mathematically. I am not using any images. I didn't use Photoshop. It's not using any program. It's just one mathematical function, a huge one, that's just rendering the whole thing. It's very low on tech stack. It's so low on tech stack, you can run it on a graphical calculator. You can run it on a Google spreadsheet. You can program it in any programming language within minutes, right? So my fascination with these started with Harry Potter, of all things. In the film, there are these images that never end. It's a painting, it's a photo. It remains distinctly the same. However, it's always changing over time. And I found that very interesting. And I've been painting for 10 years and I've also been programming. And I said, can I combine my mathematical skills and programming skills with my artistic sense to create something like this? As I mentioned before, this can go on forever and it will never repeat itself. I mean, this does. This is an animation. So why do I make these? I make these because I think it makes me a better programmer. I think it will make you a better programmer too. By the way, you will see these images. Within this attention economy, I can't afford not to show you something when I'm speaking. So I thought, wow, generative AI has come such a long way. Maybe we generate with those. So you see the prompt there. That's a programmer getting stronger. It's very accurate. We do get stronger like that. It's very hardcore. So why? Why do I think you become a better programmer this way, right? Guys, stop laughing. This is serious stuff. I'm kidding. So I think you get a better programmer, but before that, I have to explain to you how you write a code like this. Imagine you have a grid. The grid has a bunch of cells. With each cell, you associate properties. For example, the coordinate system, right? This is a 16 by 16 grid. So bottom left, I don't know who's left, but the green point is 0, 0. Top right, 16, 16, middle, 8, 8. Super simple. Now you have two nested for loops, and all they're doing is they're iterating horizontally and vertically over your grid. That means you are visiting each individual cell, right? Within each cell, you call a function called paintPixel. This function is magic. It's a black box for now. All it does, it returns a color that you assign to that cell. That's all this program does. It kind of looks like this. So you're iterating cell by cell. And one of the easiest programs you can write within this paint function is visualizing the coordinate system. So the coordinate system is going between 0 and the dimension of the grid, divided by the dimension. So now it's going between 0 and 1. You can assign the x coordinate to red, the y coordinate to green. That means the more you go from left to right, the redder it becomes. The more you go from bottom to top, the greener it becomes. And top right, where it's both green and red, you get like yellow or orange or whatever. You can notice two things about this program. First of all, this is a very stupid program. It has no global understanding. It's not dependent on anything. The result of the calculation for the cell 5,6 is not dependent on cell 10,10, right? Also, it doesn't need to access some extra class or anything like that. It's just a function. That's all. On top of that, you're calling the exact same function for each cell. You're not calling for cell 1, and for cell 3, another function. That means you have to think differently when you're programming like this. Because you want to have different output. You want to have each cell should have a different color. But how do you do the same transformation on different cells and get different output? That's kind of the challenging part. So keeping these two things in mind, that means you can convert this from a serial execution to a parallel program, to a concurrent programming. Why? Because normally, when you're dealing with something like normal programming, you have object-oriented programming and it's single-threaded, right? And there are things like racing conditions. You have to figure out how to distribute work and stuff like that. You don't have any of these problems because each function is very stupid, doesn't have any dependencies, and each function is assigned to a cell. So you can create as many threads as you want. Each thread would just, color a cell. This sounds like a very nice paradigm to do concurrent programming. It's called SIMD. We have come so far. This is multi-threading, by the way. Failed at the task. So this is called SIMD. It's single input, multiple data. So the idea is that you are applying the exact same mathematical transformation to a lot of data points, right? Where it is great, because concurrent programming could be a lot faster than single-threaded programming if you do it right. And this gives you an easy way to do concurrent programming. But as I already mentioned, it's hard to kind of program for this context. Let's go back to that single-threaded object-oriented. You have a player. The player has a bunch of methods and parameters. The player does something, talks to enemy, talks to manager, talks to audio. There's all these dependencies. There are messages going back and forth. You have access to all this memory. You have access to internal states. You can flag things. You can't do any of these things in SIMD. Nothing. You have access to none of these, right? So you need to really get creative about how you do things. Just to give you a bit of a context how important this is, GPU architectures are based on SIMD, not just GPU chips, a lot of other chips, for example, the ones for machine learning and stuff like that, based on similar concepts. So everything you can do with a GPU, VFX for games, VFX for films, all this procedural stuff. That gentleman is not AI generated, that's Ken Perlin. He won an actual Oscar for coming up with an algorithm that adds detail to a CG world, a large CG world, within the context of SIMD. Physics simulation, right? So things like fluid simulation, Newtonian physics can be a lot faster if you do it concurrent. And you can use SIMD to express it that way. So entertainment, science, weather forecasting, medicine, there is a branch of scientists that are specialized at taking a normal problem, converting it in a way mathematically, so you can run it in a SIMD context. Signal processing, procedural music, data compression, communication. That guy is doing a stellar job. That's a 10x engineer right there. So many hands. So these are some of the cornerstones of computer science in the past 30 years, right? And they can get a lot of advantage from being expressed in SIMD. So I hope I gave you a bit of a, let's say, context of it's hard, but it's important, right? So how do you practice this? Let's say you decided to take one of these domains to practice this mindset of how to program for SIMD. For example, I don't know, fluid simulation. I have done that, it's stupid. So you need 9 months to figure out the mathematics, the physics. You come up with this entire new domain. 90% of your program is single-threaded, dealing with resources, booting the program, cleaning the resources. So much overhead just to practice, right? Whereas the program I suggested, the painting program, you can do it in 10 seconds. The overhead was 2 nested for loops. That's it. And you can immediately start practicing this way of programming. Okay, mathematical thinking. That child is very enthusiastic. Yeah, mathematical thinking. It's like going to the gym. I've never been to a gym. I have a confession to make. But I imagine you go there and you start lifting things, right? And that movement you never do in real life. But the muscles you train, Those you use all the time for various different tasks. So this is kind of similar. You have to think mathematically when you're doing this type of simple programming, and the skills you train is used for your daily job, and it enables you to do more than your other programmers, like compared to other programs. This is the only slide I'm going to go on a philosophical tangent. The joy of creating art. Making art is wonderful. It's good for you. It's good for the society around you. However, it's very inaccessible to a lot of people, right? Because it's hard to sing, it's hard to dance, it's hard to draw. It needs a lot of practice. But some of the best people I know in this industry of mathematical imagery can't draw a stick man to save their life, right? They're terrible drawer. So if you are decent in programming and maths, chances are you have a new outlet, an artistic outlet to express yourself, to feel good about understanding the world around you. There is, at the center of art, there's this concept that you put aside your preconception of how the world is supposed to look like in the favor of looking at what really is and coming up with a new formalization, new abstraction, new mental models, and expressing that to others. If you think about it, this way of creating painting is the ultimate form of that. You're constantly looking around in the world around us. You look at a tree and you ask yourself, what is the essence of a tree? How can I express it mathematically in the simplest terms to get the greatest variation of what makes a tree? And that's fantastic. It's a very fun process. So I hope I gave you a bit of a background of why I do these, maybe why you should give it a try too. It could make you a better programmer. Now, a bit of a building block. I don't have time to go line by line, but I can give you a bit of like, let's say, the core concepts of how do you even approach a problem like this. The first one is the sinus curve. I hope it's not the first time you're seeing a sinus curve. If you're like, what? Look at that. That's crazy. I didn't know that existed. I'm like, oh my God, that's the wrong talk. So sinus curve, keeps blowing me away because so much of our world, so much of nature can be expressed in this simple function, from the way, I don't know, water moves, the way cloud forms, the way the ground dries, the way the flower petals form, the shells of the animals, right? All can be expressed using sinus curve. It's insane. It's amazing. Now, if you go back to high school, and that is really accurate. That is how high school felt. If you go back to high school, we had these lessons with, you could add or multiply a number, a constant, to a function, and visually things would happen to it, right? So for example, you could do, you had this f of x inside the bracket, outside the bracket, stuff happened. You also had absolute, which I'm not going to cover, that basically mirrors. For example, you can stretch a function horizontally if you multiply the x itself. So inside the function, before you calculate it, you multiply the x, you stretch it horizontally. You can do the same vertically, right? You can move it left and right. If you add within the function, you can move it up and down. These and some limited other series of functions are called shaping functions. Why are they called shaping functions? Because they enable you to mold, sculpt, and shape a function to match something you have in your own mind. And these are incredibly useful. I cannot stress this enough. They're useful not just for procedural graphic, they're also useful for procedural audio. They're useful for gameplay programming. Anytime you have an entity that is supposed to behave a certain way over a certain dimension, like time, and you're like, okay, I can imagine a mathematical function where that describes that behavior. If you know shaping function, you can create that specific function and modify it over time. So imagine you want to animate a sinus curve, and you take application time, which is the time, at the beginning of application, you boot is 0. Every frame it counts up, right? You add that within your sinus function, what do you get? You get a function that is eternally moving from right to left. That's just a line of code, and we already have animation. That's pretty cool. That's not the only thing you can do with a function. You can add, multiply, divide functions with each other, and you get a third function that's visually a combination of both put together. In physics, that's called wave superposition. When you add them together, you have one wave with a certain amplitude and frequency. You have another wave with another amplitude and frequency. You add them together and you get a third wave. And you look at that wave, it's visually more intricate. It's a bit more interesting, has a bit more detail. But you can see how that's the visual combination of both. We put that in our program, it kind of looks like this. Wow, the contrast is terrible. There's a grid in the background. Yeah, but it's not important, thank God. So, now wait a minute. I didn't intend it to be that aggressive. That was that program on its own. So wait a minute. If you look at that, it kind of looks like a mountain. It also could look like cloud. Could look like moving water, right? The way I'm drawing these, by the way, is for any cell, I take the x coordinate, I put it in the function, I evaluate that to know what height the function is at that x. Then I am like, okay, is the y of that cell below or above that? In other words, all I'm doing is asking, are you below the function or above the function? If you're below, I color you a certain way. If above, I color you in a different way. So that was a bit too soft for a mountain. So what I would like to do is switch the base function I'm using. I'm using the red function right now, which is a sinus function, obviously. I want to switch to a blue one, which is the triangular wave. The triangular wave is when you take a linear line, x equals y. Okay, y equals x. Doesn't matter, you could argue. And you, bit by bit, using shaping function, you transform it to that form. I'm not going to cover how, but the formula is there. It's a very simple formula. It just gives you an example of how powerful these shaping functions are. So I take the soft wave away, I use a harder wave, and instead of adding just 2 waves, I'd add like 5 or 6, and I'm getting something that looks quite close to a mountain. And I put it in a function. So this is an example of using shaping functions. The future examples, I'm not going to go in so much detail of how I constructed the shape, but it's very analog to this. It's kind of like a similar idea. So now that I have that in a function, I can call it a bunch of times. And each time I can adjust the height. Wow, the contrast is terrible. The height, the colors. Promise is the last time I'm going to complain about the contrast. The height, the colors, and stuff like that. But remember, these are functions as much as sinus is a function. So I can actually move it, right? I can move it and I can move it with a different speed. And that means that our brain, because of parallax, starts seeing an illusion of depth because they're moving at different speed. So that was the first building block, shaping functions, very important. The next one is the concept of spaces. So far, we have been only working on the Cartesian coordinate system. That's the vanilla coordinate system, right? It's very basic. But that's not the only coordinate system around. As a matter of fact, we constantly construct new coordinate systems because it's easier to compute certain things in that coordinate system, right? It's a whole field of science. Now, an example of this is the polar coordinate system. So the polar coordinate system defines everything with respect to a circle. For any point in the space, you draw a line from the center of the circle to the point, and you're interested in 2 properties. The distance, so the radius, or how long that line is in rotation of a circle, so the theta, the angle. If you take a simple function, y equals 1, it's one of the simplest functions you can take. It draws a straight line from left to right. And you draw it in polar coordinate, you're going to get a circle. Why? Well, because we are bending the entire space around the circle. So if you have a straight line, you bend it around the circle, you get the circumference of a circle. Super simple. What's the idea behind this? The idea is that I could have drawn a circle in the Cartesian coordinate system, but it's a lot easier to do it in polar. So we can construct a circle, construct a space, a specific space, and if you take any function and you draw it in that, it looks different. For example, the thing we were doing with the waves, that if the y is below a certain value, we color it in a certain way. That's how it looks in the polar coordinate system. It's not very clear what it is now, but it will be clear in a second. A line is not the only function we can wrap around a circle. We can wrap any function around a circle. This is a wave function I'm wrapping around the circle. The code for these, all of these, by the way, are done using this SIMD programming. Every drawing you see, and all the code is available on my website. For example, we can take a sinus function. Imagine how a sinus function looks. Squeeze it, stretch it vertically, wrap it around the circle. It kind of looks like petals of flowers. But it's not perfect. We can now use shaping function to get the shape we know a flower petal to look like. Flower petals are very thin at the top. They're the thickest in the middle and kind of thick at the bottom, right? So we are just like taking the peaks, we are actively deciding where to stretch and squeeze, and we iteratively get here. And it kind of looks like flower, but it looks too graphical. It's too uniform. So I can mess around a bit. I could say, okay, the further you go from the center of the flower, you should displace the petal more and more in the polar coordinate system using a sinus wave, right? So you get something like this, and that's kind of looking like a flower again. This is our functions, and functions take parameters. That means I can call a function again and again, and each time with a different parameter. I start getting variation, right? And I can get endless number of variation. That's where the endless variation comes from when you're dealing with these mathematical paintings. So that was the second, which was the spaces. Third comes the idea of domain repetition. It's very useful things in mathematics. That function there, fraction, is the cornerstone of computer graphics. It's insanely important, despite being so simple. This is what it does. You give it a number. Between 0 and 1, it does nothing. It doesn't touch the number. From 1, it only keeps the fractional part of the number. So 1.2 becomes 0.2. 1.7 is 0.7. 3.6, it's 0.6. Simple. What that is doing visually is that it's taking however the function looks between 0 and 1, and it's repeating that again and again and again, which is amazing for us because it's practically repeating space itself. So we had this program where we visualize the coordinate system. We can call frac on it, and you can see in the x direction, we can see these tiles, these repeating coordinate systems. But we can also do that in the y direction, and then we get a grid within a grid, right? So we're repeating both y and x. This is, by the way, how we do tiling textures in a video game. What's the latest hot video game that came out? I don't know. Starfield. It's huge, right? It's unrealistic to add and paint every detail in this world. What we can do is that we can wrap around this repeating space on any surface in the game world and repeat the same detail texture and create an illusion of continuous detail. So now we have a repeating coordinate system that is going between 0 and 1, and every function we have created so far can be called within this repeating coordinate system. For example, the sunflower. And we get this. Kind of looks like my grandmother's wallpaper. Actually look like it. But I might like my grandmother's wallpaper too. So we can now say, okay, can we fraction the space more and more the closer it gets to the horizon, right? And we're starting to get something that looks kind of like a flower field. It's a bit too regular. The flowers are not overlapping, but we can fix that. We can pack this in a function, and we can call it a bunch of times, right? And every time I'm moving it a bit left and right, I'm displacing it a bit so that they overlap, they look a bit, natural, and then I get this. So here comes the refinement phase. For example, I can say, using shaping functions again, sound like a broken record. We say the closer you get to the horizon, blend the color more and more to yellow. So it kind of looks like at a certain distance, we don't see the individual flowers anymore, we just see a sea of flowers. Or I can add noise, which you cannot even see, nice. Which is again an application of shaping functions on CNOS. Super simple function to construct. And I added a stem and stuff like that, but it's all like very simple drawing. Nothing more complicated than what I already covered. So this is basically a painting, but we can move it, and it looks like that, right? I already made the clouds, by the way. But that's the thing you can think about, based on the stuff I already talked about. How would you make the clouds? You're gonna start with a CNOS. Where would you go from there? There is no reason why you should only do this in 2D. You can do this in 20D if you want to. The concept of SIMD carries over on any type of programming, really. Here, for example, I'm applying the concept instead of 2D images, I'm applying it on 3D surfaces that I can displace around. But everything you see there, nothing is hand-created. Is it? No, it's not. Nothing is hand-created. Everything you see there, from the color, from the shape, is created mathematically, right? And that's why I can very easily convert between a winter scene and an autumn scene. Because these are mathematical functions. You can change parameters and it changes everything. This could be useful for a film or an animation or for a game. Or this one, I have I was going to say healthy, but some might say unhealthy obsession with woodblock prints and Chinese landscape paintings. And I made myself an endless Chinese landscape painting. Every time I press, it creates a different landscape painting. Because, except the calligraphy that I had to do by hand. And that's what mathematical expression can do for you, right? So that's it. Thank you. I am also, for questions, I am going to put, so basically this is the function I'm actually using. And just to show you, I'm wrapping things like triangular wave inside a simple mathematical function. But just to show you, the whole thing is less than 277 with all the spaces and redundancies. I wrote it extra in a way that people can easily follow, right? I split a mathematical function in several. The whole thing is not that much, right? So I can just play in this computer in real time. And that will go on forever. Okay, thank you.